Okay, so let me remind you what happened yesterday. Yesterday, I decided to suddenly kind of go away a little bit from what we had been doing, and we started talking about the cones of measures. And that was in order to try to prove, remember where we're trying to go, we're trying to prove that if we have a measure that has a density, we want to prove that at almost every point, all the tangents are flat. And for that, we needed the structure of cones. We talked about what a d-cone was. I defined these functions, these FRs that were not distances, but they were almost distances between measures, but only of what happens to them, measures restricted to the ball of radius r. And I defined the distance to a cone, which I will remind you of because I need that. And then we talk about, I defined this thing called the basis, which I'll remind you in a second what it is because, well, because it's not the most natural thing and because I need it. And we talked, so I define, so I was already gonna, oh yes, sorry. I'm supposed, this is an ad, okay, commercials. This is the talk for this afternoon by Mario Quillas, and it will be on the Reifenberg topological disk. And as you will see, I will refer to it and to some of the things that happened in this. I mean, I'll talk about Reifenberg today. Just, it's not that we had planned to match it, but it happened. Okay, so these guys were the radon measures. And we had talked about these things, F sub r's for F positive. And we had talked about these things, D cones. So there were cones. And they were also invariant on their dilations, okay? And we had talked about the measures nu. For the D cone, we had talked about the measures nu such that F1 of nu was 1. And I had called these the basis of M, which you might call is like the unit sphere, but for this one. And we had said that the basis was closed, this set was closed under weak convergence of radon measures, and it was compact if this had M had a compact basis, if this set was compact under weak convergence of radon measures. And I remind you, I had made weak convergence, I had metrized the topology of weak convergence, and I had made the radon measures a complete metric, a complete separable metric space with that. Okay, so that's where we were. A note: I'm gonna make a comment right now that is going to be trivial in the context we're seeing, but if I have time tomorrow when I do the applications, you'll see the relevance. Because the notion of compact basis plays an important role if what I'm going to say afterwards, but I need to give you a criteria for being compact, because of course all of you know what something, you know, what it means to be compact in a metric space, but it's not very easy to prove that a set is compact, okay? So here is a little lemma that I want you to take in good faith, but it will solve lots of our problems because then M D cone in R with a closed basis, then M has a compact basis if and only if there exists a constant k positive such that for every r positive and every phi in M, the following thing holds. Phi of the ball of center 0 and radius 2r is bounded by k phi of b of 0r. Okay? So it means that all the measures in this cone are doubling at 0 with the same constant. Particular, our tangent measures have this property. So the cone of tangent measures has a compact basis. The cone of uniform measure has a compact basis. Okay? And remember, all our cones, 0 is on the support of that measure. Okay? This is a remark that, if I have a chance, will be useful tomorrow. Okay, and now I'm going to give you Price's main theorem about connectivity of cones. I'm going to give you a warning. I'm going to write a condition. I still, every time I write these, I wonder why on earth did he write it this way. It's not a very natural condition. And then what I'm going to do is I'm going to say, well, look, this is a corollary, and what we will try to prove is the corollary. I am sure that the main theorem has way more information than the corollary. I personally have never been able to use the main theorem. I always use the corollary. And by use, mean I prove the hypothesis of the corollary. The other one is, okay, you'll see. Maybe I'm being biased and I'm destroying, if I had not said this, I'll put it on the board and you think, oh yes, this is crystal clear. I just have biased you. But I mean, it is what it is. Okay, bear with me. But this was also a warning, so that in case you don't find it crystal clear, don't worry. You can not find it crystal clear and you can stand up in front of you, a lot of people, and talk about it, and it's perfectly fine. In particular, there will be a corollary right afterwards that's usable. Okay, main theorem. And so when I call it main theorem, it's main theorem of connectivity. So this is the connected properties of cones. It's quasi-invisible here. So let F and M be D cones in R. Okay. We're going to assume that F is included in M. Okay? We are going to assume that F has a compact base, a closed basis. Now, F is closed in M, and M has a compact base. So far I haven't said anything. All of these are relatively standards. And we are going to suppose, here we go. Furthermore, suppose that the following property, that P holds. So this is property P. I decided to call it P, not David. Here is property P. It says, there exists a number, epsilon 0 positive, such that for every epsilon in epsilon 0, there is no eta in M. M is the big one, satisfying dr of eta f is less or equal than epsilon for every r bigger than r naught, and dr0 of eta f equals epsilon. Okay, I haven't given you the conclusion. I'm going to try to talk about P for a minute.
What's R0?
R0 is anybody. Okay? Basically, R0 doesn't have to be a specific somebody. Any R0, I mean, that doesn't start happening. So what does this mean? Of course, there's no conclusion yet. This is the hypothesis. So P is the condition that I personally find somewhat obscure. What the condition is saying is that you cannot find a measure in M, in the big one, which is close to F. So where are you? Sorry. Okay, so close to f from here on, and here at this point is exactly at epsilon. Okay, so you cannot be, if f, I know, and is a bias, there are examples where this has been used for f that are not flat, but since f and flat start with the same, I mean, it's the same letter, let's assume there is no measure that is flat from close to the flat cone from here on, okay? That is exactly at here, and then still is less or equal than here. It's a very awkward thing. I will give you a corollary that is, you know, it's just a corollary, but it will be clearer. But so if you assume that such a measure doesn't exist, okay, then the following thing holds. Then, so this is the rest of the thing. For any radon measure mu such that all the tangents of mu at A, so for a radon measure mu and A in the support of mu, if the tangents of mu at A are inside the bead cone and the tangents of mu at A intersect the small cone, then the tangents of mu at A are completely contained in the flat cone. Okay? Okay.
What is R0?
Any R0. Okay, so what does this mean? There exists an epsilon 0 such that if there is, no matter who you choose as an R0, you cannot find a measure such that at R0 is exactly at distance epsilon, and from there on is at distance less or equal than epsilon. Okay? The reason is, to some extent, what you end up having to prove is that if you are less or equal than epsilon, if the distance is less or equal than epsilon from some point O, then you had to be flat. You had to be in F. And therefore, you cannot be at distance exactly epsilon. Okay? So that's what this condition is asking you to prove. But this is a hypothesis. This is not a conclusion. Okay? It's a hypothesis. So let me give you a corollary to this, which is what we will apply. Okay? A corollary that hopefully will be clearer, which is, of course, also a theorem, not a corollary, but it doesn't matter.
So isn't this condition like saying that f is closed with respect to the distance, in a way?
It's way
You
more.
can't approach it.
No, it's more than saying that f is closed, because when you are close to a set, you can be at distance epsilon. This is saying roughly that if you approach f too much at infinity, you actually had to live in f. The only way you can approach f at infinity, and that's why it means r bigger than r0, is you have to be already in f. And therefore, that's why that could not have happened, that you were at distance exactly epsilon from f. The flat, under this condition, you're asking that your cones absorb everything. But it's a hypothesis. So you're going to have to go and figure out when you can prove this hypothesis. Okay? In some sense, so you'll see. I'm not going to give you an idea of how this proof goes. I'm going to give you an idea of how the proof of the corollary goes. That is actually straightforward. Once I tell you how it goes, you're going to sit down and you're going to do it. Now, the key point is you have a tool. How on earth do you prove that the hypothesis of the tool is satisfied? Because, you know, it's one of those theorems where you have this beautiful result, but you have to satisfy the hypothesis. And that's what the work of Price's paper. So this is in section 2, section 3, and then the rest. Section 3 proves these for a special kind of measures, and the others prove it for other measures. Okay? The rest of the paper is designed to show that property P holds for the cases he needs. Okay. So let me give you the corollary, which hopefully will be cleaner. you know, it's, I don't know if David wrote it like this, but it doesn't matter. It comes out of his work, okay? That F and M becomes, same as before, F and M, F relatively close, and M compact bases. And we assume the following. Moreover, we assume that exists epsilon 0 positive such that star holds. If dr of eta f is less or equal than epsilon for some r less or equal than r0, and r0 is anybody. If from some point on you are at distance less or equal than epsilon 0, then eta has to be flat. So this is our hypothesis, that once you approach f enough, at infinity, you live in it, okay? You cannot. So this is a hypothesis. And then the conclusion is the same. Sorry. Then for any radon, measure mu, blah, blah, blah. Okay, sorry, it's horrible when the person on the board uses something that's already written, and then if you're trying to take notes, you have to rewrite everything. But this block now goes over here. Okay? So let me give you an idea of why star implies this. Okay? And then I'll give you an idea of how we're going to use it. And then I'll show you that the idea is very nice, but now implementing the idea is a little bit more elaborate than it appears. Okay? Questions before I? Okay, so we assume that stars holds. We assume that the tangents are inside M, and there is one tangent that is in F. And we want to prove that all the tangents are in F. So we assume that that's not the case. Okay? F is closed, so there's somebody in F minus there's some, so if F is, there's somebody who is a tangent and which is not flat. Okay? Somebody, F is close, somewhere in this hypothesis here. Therefore, kind of it's far away. Okay? So you have one tangent which is very close, which is flat. Let me call F flat even if it's not flat. And you have one tangent that's far from flat. Okay? Therefore, and what's a tangent? The tangents were all obtained by taking sequences. So you have a sequence that is going to the flat measure, and you have a different sequence that's going to the non-flat measure. And you believe me that if you're careful, you can interpolate in between these two sequences. I won't do that, but that's exactly the idea. You interpolate between these two sequences to construct a measure that is in between. Okay? And therefore, and you can put it very close to the flat or very close to the non-flat, but since it has a piece of the non-flat, it's really not flat. And therefore, you will be able to construct a measure which is close to flat all the time, but which is not flat. And that contradicts the hypothesis. Okay? So that's how this is used. So consider that the proof of the corollary. And you can really do this interpolation between these two sequences clearly, and it's not a complicated argument. You can find it either, well, you find one argument in Price's work, and you find another one in my work with Price and Koenig. And that's not the, I mean, that's not the important part of the proof. So what, yes?
So is the space of tangent measures like path connected in some sense?
It's not, it's more than path connected. It has a, once you approach it, you're absorbed by it. I mean, it's somehow you cannot, under these circumstances, you cannot be close to
No,
this.
just like in general, like regardless of like the flat stuff.
These properties, there's something hiding here which is important. So it depends who your measure is. Okay, so for the measures we have seen in some sense, yes. Okay, but if you come from other measures, no. Okay. Okay. Yeah, and then maybe tomorrow I'll say more about that. Okay. Okay, so let me try to say how we're going to use these. Okay, so why did I put these on the board? Okay, so let's go back to our problem. With our problem, so we take a break from here for a minute. Where are we? We have this measure where this density exists and is positive and finite almost everywhere. We look at the tangent measures, and almost everywhere, nu is n uniform. Okay? Moreover, we prove that for almost everywhere, if I call now f is going to be f of m n, the flat measures. So remember, this means all flat measures. So Hn restricted to any n plane in Rm and a constant. So this is a set of all flat measures. And one of the things we prove is that this thing intersects f. Okay? So have a good candidate for f. Check it out. I had the good idea of call it the same letter. Okay? So f. We are going to apply, so the idea is apply the theorem, apply corollary. Now I have to cook up m. So m is going to be the n uniform measures. The n uniform measures include the flat measures. Okay. A flat measure, the flat measures are the closed, because let's take a sequence of flat measures that converges. So it's a sequence of measures of this type. So you have a sequence of n planes. The Grassmannian is compact. There's a subsequence that converges. Okay? And of course, there's the issue of going to 0, but is relative. We are only looking at the bases, so C is not 0. Okay? So it's close. The fact that the n uniform measures have a compact basis comes from that. Because remember, if you're n uniform, phi of b r is c r to the n, so that constant doesn't depend on anything. That constant happens to be 2 to the n, the k over there. Okay? So f is closed. This has a compact basis.
Uniform measures with 0 in the support.
Yeah, but all my cones have 0. Yes, everybody now has 0 on the support. Yeah. But I remind you that for any of these guys, 0 was on the support. So yes, uniform with 0 on the support of eta. Okay? Perfect. So if I prove star, okay? If I prove that this condition holds, we're done. Because the tangents are all n uniform. So with this notation, I have the tangents of mu and a are inside M. They intersect F, and if star holds, then they're all flat. Okay? I know, there's an if. And I'm going to take two, so it's going to take me 3 hours to fill in the if, okay? But it took Price the rest of the paper to fill in the if. Questions? So is it clear how the argument goes? I mean, of course, it's not clear how we prove start, but is it clear that if we prove start, we have what we want? I have the feeling that it's not as clear to you as it is to me. So it's a good time to ask me questions. No, but you're saying yes, but I'm looking at the group here, and they're saying no, even though they're not saying anything. How about you? I mean, I would like to, I understand that the mystery of how this is going to come about, I mean, it's there and that, but what I would like to make sure is that at this point, so what do I want you to get from here? Well, this, I want you to get that this was kind of, once you put this corollary, if one fills the hypothesis of the corollary, it works. But I also would like you to see that there might be other properties. As I said, this has been used in other situations, okay? And that means with other types of cones, where this was not necessarily the flat ones, but let me give you an example. This was used by my student Matthew Badger to prove that if here you have the harmonic measured corresponded to the positive side of two homogeneous harmonic polynomials, and here you had a larger set of homogeneous harmonic polynomials, something similar happened. You could use the same technique. So what I'm trying to say is that these, which seems like a very abstract thing, can be used in different settings. That setting was a free boundary problem for harmonic measure. Okay, so it's a big tool. And at this point, the only thing I have done is like when I give you a cooking recipe that says, take the ingredients, put them together. Okay, I haven't told you where to buy the ingredients. And there's one that's a mysterious ingredient, and that's the one we'll talk about. Okay?
So maybe this is like a stupid comment, but is this kind of in the same spirit as like, you know, one sort of corollary of like Allard or Brachy's, that like you have this kind of gap where if the density is like close enough to 1, then you're actually like flat.
S1, exactly. This is a gap. What I would love to be able to tell you is what the size of the gap is, which is the epsilon 0. In codimension 1, we know what it is because I told you what the uniform measures were. They're either this one or this one. Okay, so that's square root of 2 over 2. But in general, I don't know. Okay? But it's exactly the same. Philosophically, it's the same thing. Okay? The difference is that there you have an analytic machinery that tells you if my quantity is small now, it's going to get smaller and smaller and smaller. Okay? Here it is not the same. Okay? It's a slightly different. And there in that property, basically it tells you if it's small now, it's smaller and smaller and smaller. This one tells you if it's small now, it was actually 0 then. But it's philosophically similar. Okay?
I'm sorry, I think this will be very stupid, but I think I'm a little lost in notation and terminology and maybe it's worth asking anyway. So can you say this in simple words? And
Yes. I'll be glad to tell you. Okay, we have two cones. I have the first cone is the flat measures. They're called F.
which are like
Flat.
spaces of dimension n.
On this one over here.
Yes.
Okay, they're flat. The other one, M, is the n uniform. So they're measures such that the measure of the ball of center x and radius r, when x in the support, is a constant times r to the n. Okay? I know that there are others that are not flat. I cannot tell you who they are, but they have that property. Okay? All the tangents live at n uniform. That was one of the things I proved at the beginning of the week. I don't remember what. The other thing we know is that there's one tangent that is flat. We proved that yesterday by proving that tangents to tangents were flat. Your tangents, therefore, there's one tangent that's flat. Okay? So I am exactly here. And I want to conclude this. And to conclude this, I just need to check the hypothesis. Okay? Now, we are going to, before trying to check the hypothesis, which is what will happen tomorrow, we're going to understand the hypothesis. Because the hypothesis says that, but what on earth does it really, really say? Okay? So what I'm going to spend a lot of the time now doing is understanding that hypothesis. What's hidden? What on earth does it say there? Where we're going to take f, the flat measures, really the flat ones. Okay? So now we're going to start computing. We are going to compute this thing by hand. And we'll see what happens. Okay? And then any other questions? Yeah. But if f is equal to m, then so if f is equal to m, then I'm not saying it, then this is relatively useless because let me go up again. Because what I want to conclude is that the tangents are all in M. But I have to assume that the tangents are all, I want to assume that all the tangents are in F. But I have to start assuming that they're all in M. So if F and M are the same thing.
For this conclusion, that's not interesting.
But that's the conclusion I want.
It means maybe that in dimension 2, they are the same, or is that true?
But I have to prove that. I have to prove that all two uniform measures are flat. Yes, and I haven't done that yet. Okay, that will be the simple case of what we're going to do tomorrow, and therefore it will be left to you as an exercise. But for that, I still need to show this thing over here. Okay? Okay, so let's try to understand the hypothesis. And so, for the rest of the lectures, F are going to be the flat ones and flat measures. M are going to be the n-uniform. And we are going to compute dr of eta. Did I call it eta? You know, my notes, I'm sorry. In my notes, I call it phi. So let's, to avoid, we're going to compute this. Remember what this is. This is the nth over all psi, which are flat, of fr of phi over the phi r phi psi, where fr of psi is 1. Okay? And we need to compute that to be able to understand what on earth are we talking about. Okay? So, first thing I'm going to do is I am going to compute fr of phi. And I told you that you can, I know this was written in terms of what happens with Lipschitz functions, but I said if you look at it a little bit, this tells you this is the same thing as this. Okay? So this is the integral over r of r minus z, the positive part, times d phi. Key point, I mean, this is a radially symmetric function. Okay? Therefore, we're going to integrate. let's do the integrals. So this is the integral from 0 to r of phi of the set y, where I could have called it z, where r minus y plus is bigger than t dt. Okay? And this is the same thing as the integral from 0 to r of phi of y. Y is less than r minus t dt. And this is the ball of centered r minus t. Okay? And this is a uniform measure. So I know that this is simply c, the integral from 0 to r. I'm going to call it c sub phi, the constant that I put in front of the thing. This is r minus t to the n dt. And if I didn't make a mistake in doing this computation, and you never know, but you check it, c of phi r n plus 1 over n plus 1. Okay? And this works for any n uniform measure. So in particular, I want to understand what phi looks like, c, sorry. So I'm going to choose this c. Now let's take a c that belongs to f, is n uniform in particular. So c is of the form h sub c, c, hn restricted to some n plane. And what I am interested on is on finding c. Okay? And you'll see why, because I need to compute that number precisely. So the fact that f r of c, which is like in this case, I should have put a different number. You see. So what was c of phi here is the constant in front of the measure of the ball. So with that notation here, I have c, this c over here, omega n, the measure of the unit ball in Rn plus 1 over n plus 1. And I'm assuming that this is 1. Okay? So in particular, I have a very specific value for c. Sorry, I cared about that number. I mean, it's for once I cared about the numbers. It matters. Okay? So tells us that phi is actually, c is actually n plus 1 over omega n r to the n plus 1 h n restricted to v. Okay, some v. And now we are going to compute this distance. Ready? And so we take an f that belongs to LR. Let me remind you what it is. That's a Lipschitz function supported on the ball of radius r, Lipschitz constant less than 1, and f greater or equal than 0. And I am interested in computing the quantity that comes from there. So in order to compute that, I need to compute f d phi over phi r, phi r of phi, I'm sorry, minus the same thing for c, okay? Well, no, let me put c first. Deep C, okay? And maybe I should be careful. I'm going to write these. You're going to, is n plus 1 over omega n plus 1 r to the n plus 1, the integral of f. So I'm going to do something. You realize that once this is what happens for the f r of phi, but if I multiply phi by a constant, the constant disappears. So I do that so I can put this thing in front. D of phi minus, so this phi might not exactly be, is just a multiple of the other one, but f dh restricted to v. Okay. And I'm having a minor question about whether I really have this guy here or not, but it doesn't matter, it's a constant. Okay, so this is, and now to compute this, I need to take the sup over all of these functions f. Okay? So I take the sup over all f's, sup over all f, and then I need to take the inf over all v's. I accept a question. Thank you. Here? Here? It says r minus z plus. Huh? On the ball of radius r and center 0. Okay? So this is the, I think of this as the distance from the function phi. Huh? It's positive, yeah. No, I don't, sorry, no, I don't need the positive part. Yes, sorry, I could, yeah. Yeah, no, sorry, I removed the positive part once I restricted to that thing. Sorry, yeah. Okay, so now this is the sup, so that's the distance between phi over f r of phi mc. And now remember, when I take the distance here, I need to take the inf over all c's, and that's the inf over all planes. Okay? So I know it's a pain, but it is what it is. Inf over v, and here, sorry, I poor planning. Inf over v. Okay. What on earth have I done? Well, I wrote this thing. It's complicated, it's a mess. I'm trying to get an expression that will allow you to see something. I'm going to choose my f. Okay? So I know that no matter what I put here, so I'm going to assume that this is whatever this is. I want to choose this for some f. So remember, what I am assuming in my star is that this is going to be small. So this is dr of c f. Okay? And what I want is choose a specific f and say, well, for the specific f, this is going to be greater or equal than that f. Okay? So here's the f I want to choose. F of x is the distance from x to v. I don't tell you which v, it doesn't matter for now. R minus x plus over r squared. Okay, let's check. This function is not negative. This function is the product of two Lipschitz functions. This Lipschitz function here, this one has Lipschitz constant 1, and the maximum distance from x to v, remember on the ball of radius r is r. Okay? So you show this part here, the thing that comes out of here, because we have an r squared, has Lipschitz constant less than 1. This piece has Lipschitz constant less than 1. Okay, so this function I claim is an LR. And I cut it here so that it's supported there. Then, okay, I want this function. I'll let you check that this function works. And I plug it in here. Okay? And so for sure, this thing here is bigger than, and I'm fixing my v, so we'll deal with that inf of v in a minute. That's bigger than n plus 1 over the omega n Rn plus 1, the integral of this f, distance of x v squared, r minus x over r plus and square. And that's great because I chose it so that this piece is 0 here. The distance from a point on the v, you see, this v and this v are the same, so that is 0. And I say, well, on the ball of radius r over 2, so what do I have here? d of r cf is bigger than this integral on the ball of radius r over 2. And on the ball of radius r over 2, this is bigger than 1/2 for the constant, I don't know, 1/4 something. Okay, so this is just a constant, and apparently I'm going to give you the number of the constant here, is a constant that depends on n, 1 over r n plus 2, the integral over b r over 2 of the distance from x to v squared d dx. Okay. And this is true for every v, in particular for the inf. So what have I done? What on earth did I spend, 20 minutes doing? The following thing. Once you see at the end, hopefully it's going to look very nice. Remember, I'm trying to understand this condition. Yes, Danny. Huh? Oh, no, well, I'm about to put the infimum. Sorry, I should have put one. Yes, you're right. Yes.
The quantity is greater or equal of the right-hand side is before taking the equation. So it's not just the difference of the two integrals.
So, yeah, so what happened, what I should have done is I was trying to save Blackboard, but clearly, now, what I should have done is I should have, before I put the soup, I was just doing this computation here, okay? So this computation amounts for this particular function f is this thing, okay? Then I notice that then I take the infimum, and then I can take the infimum here, okay? Does that make sense?
No, it's good.
Yes? Okay, so last time, now I'm going to leave it up there, okay? Because it's nice, but I'm about to break it. Okay, what have we done? Remember, this is the condition I have. Let's now stare at what that condition says. So star implies, later on, hopefully I'll have a chance to prove that it's basically the same thing, but let's not worry about that. Star implies the following thing, that if we look, and I need to get my constants correct, that basically 1 over r n plus 2 inf over all v of the integral of the distance from x to v. So v belongs to v in g mn squared d phi x is less or equal than a little constant depends on epsilon 0, epsilon 0 squared. This one. Okay? So the first piece of start. Start implies this. So if we can prove, so maybe I should say dr of phi f less than epsilon 0 implies this. So if we can prove that this implies that this phi is flat, then we're very happy. Remember, phi is n uniform. Now we're, so if we can show, so what we want, so enough to show that there exists an epsilon 0 positive such that if phi n uniform and this holds, then phi is flat. Okay? That's all what we need to show. Okay, I want to make a few remarks over this. So the first remark relates to Josh's talk yesterday. If you think of it, this condition here, this number over here, forget the coefficient. You didn't see the coefficient because he took, sorry, this is the ball of radius r. He took r to be 1. But this thing, this distance to a plane, was the thing that he had. So yesterday when he was looking, he was trying to estimate the distance between the density ratio and 1. Two terms up here. The L2 norm of the mean curvature and this. This quantity, also, if you come from a different branch of GMT, if you come from uniform rectifiability, what should be kind of doing like this is the beta 2 have appeared. If you don't know who a beta 2 is, that's a beta 2. If you've never seen it, who cares? Don't worry, ignore it. But if not, what this is telling you is that if the beta 2 at infinity is small, then the measure is flat. Okay? So this is a translation. So what we are going to focus on now is in this. We say it's enough to show this. We are going to show this. Okay? And so maybe before I do anything else, this will be I just realized the time. Let's take a tiny break, and then I'll come and we'll keep on going. The first thing I'm going to do is I'm going to translate this into something a little simpler, and then we'll try to prove that. Okay? Okay, so actually before I do anything else, let's stare for a second, and especially if you have never looked at these at this condition, you might not see what it says or it doesn't say. So of course it says that every point in the support is close to the plane V, every point, in an L2 sense. Let me tell you something that could be happening that will be really annoying for what we're going to do afterwards. Okay? Let me give you an example of something I don't want. So let's assume we're in dimension 1, and let's assume if the measure were simply supported, so this is the real line, and it could happen that the support of my measure is only in very little pieces. And so there, the distance between the support and V will be 0, and I will be full of holes, and I will lose control. Remember, I'm trying to prove that this thing is flat. Okay? And flat means it's supported in the whole line. And so clearly, the fact that this number is 0, even if that this is very small, even if it were 0, if I were full of holes, the real line full of holes is not the real line. So that's one of the issues. That's one of the first issues I'm going to have to deal with. And for those of you who work with these numbers, and I must confess that was something I had not paid enormous attention to before preparing for these things. To some of us who work with these numbers, we are used to the fact that there are holes, and the holes don't bother us because we just want to prove something else. Doesn't matter, okay, for us. But in this case, when I'm trying to prove that I'm the whole line, if I'm full of holes, I have problems. And so if you have never heard the next few words, what I'm about to say in a second, just ignore it. But what basically happens is that if you n uniform and you have a B2 control, you actually have a good bilateral control. Okay? So the bilateral betas are also controlled. But we'll talk about that. But so why do I say this? For those of you who are going to go to the talk this afternoon and are going to hear about Reifenberg, basically you'll see, if I have time today, you'll see something like that, that we will prove that a measure, if I have an n-uniform measure which satisfies this property, these holes are not here. But a priori, I'm worried about those holes. Okay? Okay. Now the truth is I'm not going to be able to prove these in the next, even tomorrow. I am going to do something else. Namely, I'm not going to prove it for every n-uniform measure. That would require the full force of Price's work, which will require understanding all the moments, well, not all the moments, but up to the moment of order 4, which I don't have time to do. I mean, it's really not. So what I'm going to do is I'm going to actually do the first thing that David did, and we'll prove it for a very special class of measures, n-uniform measures. Okay, so let's think for a minute. What this is telling me, the condition is telling me that over there at infinity, this thing is flat. Okay? Therefore, if I were to blow down, I have been blowing up, okay, which is little, but basically what this should be telling me is that if I bring the thing from infinity all the way here, I'm going to get something. So now, the same way we've talked about tangent measures, now I'm going to tell you what the tangent measure at infinity is, and we're going to see what this condition means for the tangent measure at infinity of phi. Okay? So let me define this. Definition. So it's a definition lemma, okay? I'm gonna put a lot of things in here. So phi n-uniform. There exists a unique lambda n-uniform such that for any x that you choose in Rm, actually maybe in the support of phi to be precise, if we look at r to the n tan tx r of phi, okay? And I now let r go to infinity. This converges to lambda. Okay. The fact that when I let r, when I take an x and I take a sequence of r goes to infinity, this converges to something is standard. It's the compactness theorem. The key point here is that no matter who my point x and no matter who my radius sequence is, I converge to the same thing. Let me give you a justification, not a proof. Okay? Let's take this one, which is the only other support of n-uniform measures I have. Of course, if I take this point, you believe me. But the point is, let's assume I take this point and I take a very large radius. In the long run, I lose everything like this. This is a large radius. The only thing I see is the cone part. So that's why I always converge to the same thing. To prove that this is true, that I only have one limit. So while the tangents at the point can be many, the tangents at infinity, there's only one. This requires the moments. Okay? It's a theorem. It's not an easy fact. But one of the advantages of these is that then for every t positive, lambda positive, lambda of t of a is t t to the n lambda of a. Okay? So this is a cone. It's truly a cone. I'm going to write it here. And basically what I want to say, if x belongs to the support of lambda, tx also belongs to the support of lambda. What I have done by doing this, before I had an n-uniform measure, anything. And now I have transformed it into a cone. And that changes everything, you'll see. Okay? And now I'm going to write a definition. We say phi, so this is the definition part, phi n uniform is flat at infinity if this lambda, okay, if lambda is flat. Okay? Okay. And so you realize maybe I should emphasize, no, I already put it here. So this is an n uniform measure. So what I'm really going to do tomorrow is I'm going to prove that if I have this type of n uniform measures, okay, these ones, and if I assume they're flat at infinity in this sense, then they're really flat. So tomorrow I will show, not for the any phi n uniform, but for the n uniform measures obtained this way, that this implication is true. And I'll tell you from there how you get to the regular phi. Okay? So that's what we want to do tomorrow. What I want to do today is keep on trying, so maybe so that it doesn't feel like there's not a single big theorem that we can grasp, I'm going to state the theorem, but rather than keep on working on the theorem, what I want to do is I'm going to spend the rest of the hour after I read the theorem trying to understand what on earth can I get out of here. Okay, there's lots of information hidden in n uniform and here, and I need to exploit it to be able to conclude something else. But so that we at least know, so this is so that you know where we're trying to get. So let me write the theorem I want to really prove, or I want to tell you I want to prove phi n uniform, so that also you have a picture in your mind of what's coming. 0 in the support of phi, then 1. If n equals 1 or 2, then phi is flat at infinity. 2, if n is bigger or equal than 3. There exists epsilon 0. Epsilon 0 depends on n and m, okay, such that if for each r bigger than r0, the number I have over there, 1 over phi of b sub r, 1 over r, phi sub 1, r to the n plus 2, the integral over br of distance of x v squared. This is an inf over v d phi. If this is less than epsilon 0, then phi is flat at infinity. Okay? In the sense, i.e., in these two cases, that means lambda is flat. Okay? That's what I want to prove. And that's what we will talk about tomorrow. But before being able to do that proof, we need to understand that property. Okay. So I'm going to do two things now. The first thing I want to prove is I only have something that appears to be close in L2. I'm going to show that I am close, that every point in the support of phi in the ball of radius r is close to a given plane, to a specific plane v. Then I will prove that there are no holes. Okay? And I think that's what hopefully I'll be able to do today. Okay? So the first thing, I know it's late, we're going to apply Chebyshev. That we all feel comfortable with. Yes?
Is it that is P of B1 or from her?
No, B1. The R is tiered is because I am putting a uniform guy, and remember the fees measure different things, so I have to have a one. Okay. Okay, so let's try to understand my start there, and let me do something to simplify my life. We're going to assume that this whole thing is C0. Okay. And we're also going to epsilon 0, and we're also going to assume that we chose a good plane so that we are close enough. And of course, this epsilon 0 is not the same one I started with. This epsilon 0 is 17 times the epsilon 0 from before, but that doesn't matter. Okay? So what can I get out of here? And once again, I erase the BR. Okay. So let's call G sub R the set of X that belongs to the support of phi intersection BR. Sorry, let me do it correctly. Where the distance from X to V is less than epsilon 0 to the 1/4 R. Well, by Chebyshev, you know that the complement of this guy is big. So you use Chebyshev and you obtain something along this line. So Chebyshev BR minus GR is less or equal than epsilon 0 to the 1 square root phi of BR. Okay? So this is a very big set. Okay? Just Chebyshev. Okay, let's take a point that's not there. Okay, so let's take y. And I have to be a little bit careful of where I choose my y. So I'm going to draw a picture so that you see I'm not doing any, I'm being sneaky. So I want to choose a y that belongs, I want to guarantee that is in a ball a little bit less big than R. So is R, what did I call it? 1 minus epsilon 0, 1 over 4n. Sorry, don't worry about that too much. Minus g of R. So what I'm doing is I am on the ball of radius R here. So this is 0. This is R. I want to choose a point that's not in the good set, but that is well enough so when I look at the distance to the boundary, it gives me the distance to the good set. So I choose it here. And I claim that there is a rho positive such that B rho of y is inside BR, okay? Intersection GR complement, but B rho of y intersection GR is not empty. And hopefully I put a less or equal here. Okay? So what does it mean? I have my good set. This is my good set. And I choose a ball, and this is the distance of the point to the good set. What I'm trying to show is that for everybody in this ball, not necessarily in the whole ball of radius R, but in a slightly smaller ball, I am close to this plane. Okay? So I'm trying to prove, for those of you who are familiar with these, that the beta 2 gives me a beta infinity, which is not unusual for an Alford's regular measure, for those of you who are familiar with that terminology. Okay, but that's okay. Oh, the only thing that I have done here is so since phi of BR is included, B of rho y is included in this measure is less than phi of BR minus GR. This guy happens to be epsilon 0 to the 1/2 phi of R, and this happens to be the same thing as phi of, not phi of BR. Did I write? Yeah, phi of BR here. And this is n uniform. This is phi of B rho. This is a constant. The constant is the same. This gives me rho to the n has to be less or equal than epsilon 0, 1 over 2 R to the n. And it tells me that rho, therefore, is small. So the distance of any point to the good set is small, epsilon 0 small. So that means that the distance from this point y to the plane, well, is like the distance of y to the good set and the distance of the good set to the plane. Okay? So, abusing notation is a little bit. V is less than the distance of y to gr plus the distance of gr to v. We have to make this precise, but that doesn't matter. This is rho, which is epsilon 0, 1 over 2n r. And this here was epsilon 0 to the 1 over 4 r. And let's assume that n is at least 2. So this is 2 epsilon 0, 1 over 2n. The key point, okay, let's ignore the epsilon 0 to this power or that power. The key point is here is what we're able to prove. That out of here, for every y that belongs to that ball that I just erased, the distance between y and v is less than that number over there, 2 epsilon 0, 1 over 2 to the nr. Okay? So I started with an L2 bound. I have a pointwise bound. Remember, this still could be that this is 0 and I'm full of holes. Now I need to address the holes. Okay? I need to show that I don't have holes. Questions? Okay. So what does it mean I don't have holes? It means the following.
Can you
Yeah.
remind me what are the holes now?
Sorry?
Actually, I got lost. What are the holes here?
Oh, what? No, there are no holes, fortunately. But look at what this means. This, I'm saying that the support of x is close to a plane V, okay? In an L2 sense. All of these computations was to show that it's close also in an L infinity sense, pointwise sense. But still at this point, it could be that the support, let's assume V is just the line. It could be that the support looks like that. It's on a line, but it's just full of holes. And what I'm trying to prove is that the support is a line. So if I have holes, I have issues. You agree I could have holes. This distance will be 0, but I will have all of these holes.
Otherwise, uniform measures can have holes.
Now that's what I'm about to prove. That flat uniform measures cannot have holes.
Without
It depends exactly what you mean by uniform. If you mean, and what you mean by holes. In the sense that, no, you see, because it could be, if you're not flat, then I don't have to constrain myself to here. So if I don't have, I cannot tell you that I don't have a uniform measure that is supported in these. And then do I have holes? No, I don't think I have holes, but if I look here, I appear to have a hole. So we will have to think what you mean by holes before I answer that question. Okay.
the initial this dashed line is just the path to measure on V.
No, what I'm thinking is I am trying to prove, remember what I'm trying to prove. I'm trying to prove that phi is just, let's say, Lebesgue measured here. Okay? Out of here, I have gotten, I'm very far, I agree. I have proven that the support of my measure is close to the plane. At this point, I don't even know that my measure is not full of holes. And I'm interested in knowing that I don't have holes. My next step is I don't have holes on the support. Okay? So I'll show you, I'll do that. Yes, there was another hand up.
Well, in this step, you didn't even use specifically uniform, just the density ratio. So
I'll force regular. Yeah, but since I haven't used that terminology, I use here the fact that, yeah, but yes, you're completely right. Okay, so, if these were a different crowd, I would never have done that because that's a standard thing, but I am imagining that not everybody had seen this argument before, so that's why I did it. And also to get you ready for the next one. Okay, now we don't have holes. Let me state what does it mean we don't have holes. So lemma. For every tau, when do I start negotiating the extra time? Because Joshi negotiated his extra time at the very beginning. So I'll let you think about it. Okay? For every tau, there exists an epsilon 0 such that if phi is n-uniform, with phi of the unit ball equals to 1, so I don't have to keep on dividing, 1, sorry. And, of course, 0 belongs to the support. And the integral over b1 of the distance of x phi squared d phi is less than epsilon 0, okay? For some v and g mn. Then, and I'll draw a picture in maybe for every z that belongs to v intersection b1. So let me draw. We have this plane v, and we have the support, we have phi. And what we have proven is that, and this is the ball of radius 1, that the support of phi lives somewhere here. Okay? I don't know where, but somewhere around there. And I could possibly have holes. And look what this says. It's for the first every z in v intersection b1. B, the ball of center z and radius tau, the one I chose. Okay? Intersection the support. Okay, so I chose my tau, I choose my thing. And it tells me that when I do this intersection, this is not empty. Okay? So basically, what this is saying is that if I'm willing to assume that in an L2 sense I'm close enough to a plane, the plane is also close enough. Okay? And so for those of you who are familiar with these, or to give a preview of what's going to happen in the next talk, what this is telling you is that the Hausdorff distance between the support of phi and v in the unit ball is less than the maximum between tau and 2 epsilon 0 to the 1 over 2n. Basically, that at this level, the thing is Reifenberg flat. Okay? Okay. I'm going to be honest with you. So yesterday, I was telling Hervé, when I finished, I realized, oh, God, I need to prepare some more. I was taking Severine. I was like, I'm going to need to prepare some more for Friday because clearly I'm going at a speed that, I'll be able to say way more than what I planned. Well, let me tell you, now I'm concerned I'm not going to be able to finish what I had initially prepared, let alone the extra things I prepared. So I'm going to take 5 more minutes that you have nicely allowed me to have. Thank you. And so, thank you. But he took 5 minutes. It would be really unfair if I didn't get them. Thanks. Okay. So. Wow, but now he might get offended because you're showing preference there. So we don't want to think that you're taking. Anyway. Okay, thank you. So what do we do? How do you prove something like this? By contradiction. Assume not. Okay. What does that mean? That there exists. I'm just going to write it very briefly. What the contradiction means, and then I'll wave my hand explaining what's happening. So by contradiction. Huh?
What is the goal now?
I want to prove this lemma. Okay? And the reason I want to prove it is because if you work in this field, proving that something doesn't have holes tend to be complicated. Okay, and here it comes almost for free, but you know, I'm very biased. I present the things that I know are hard in the field, at least from my point of view. And yeah. The issue of whether something has holes or not has played an important role in some areas of geometric analysis. That's why I want to show this one. So assume not. So that means that exists a tau 0 such that for every k, the following thing happens. So if not, for every k, we can find a phi sub k n uniform with measure of the unit ball equals to 1 and a plane v sub k, okay, such that the distance in B1 of x v sub k squared d phi sub k is 1 2 to the k. I think I like that. V sub k, of course, is a plane. And we have a bunch, and there exists a zk that belongs to vk intersection B1 such that B of zk tau intersection the support of phi sub k equals empty. Okay, that's my contradiction. Okay, what happens? Well, the v sub k's are n-plane in Rm. Grassmannian is compact. There's a subsequence of the vk's that converge to something. So we're going to make the list of things. There's a sequence of vk's that converge to some v infinity. The zk's are all in the unit ball. There's a subsequence of them that converges to something. We, of course, choose the subsequences correctly. So these converge to z infinity, which belongs to v infinity intersection B1. The phi sub k's, they're all n uniform, and the measure of the unit ball is 1. Therefore, they're uniformly bounded on compact sets. So there exists a subsequence of them that converges. Weakly. Okay? Because I don't want to overstay my welcome, I'm only going to say something. I won't prove it. If any of you want to see the proof afterwards, just let me know. So I do the projection. I'm going to consider another set of measures, phi sub k's, which are the projection into, I call it vk, of the function of the phi sub k. Okay? Did I call? Let me see if that's the way I call it. Restricted of the phi sub k. Okay? So basically, I simply do the projection of this measure. This is very close to flat. Okay? I can prove also by passing to a subsequence, and that what I can prove about this one is that the distance between phi k and phi sub k converges to 0. These ones are also uniformly bounded, so they converge to, C infinity. And this C infinity, I can prove here. So I should prove here. F1 goes to 0. So this means that F1 of phi infinity, C infinity, phi infinity is 0. Let's see where this one is supported. Remember, these ones, they're projected onto VK. So this one is going to be supported in, so this guy, the support of this guy is V infinity. Everybody, I should have said, this one is n uniform. This one is n uniform. What?
Subset of V infinity so far.
Oh, sorry. You're correct. It's after this one. N is n uniform. I leave it to you to check that the only n uniform measure supported on a subset of V infinities Rn is Lebesgue measure, modulo a constant. Okay? And if we're going to be super precise, this is in the ball of radius 1. Okay, because all of these things happen only in the ball of radius 1. Okay, I leave it to you to check that. And that's my contradiction, because when I look at these, one of the properties is this translates. So from here I have that B of Z infinity tau intersection the support of phi infinity is empty. Maybe tau over 2 if we want to be really, really very tau 0 over 2. So this one intersection the support of this one is empty. But these two things are the same thing in B1. And the support of this one is all of the ball. So I cannot be the whole support and have a hole in the middle. So that's a contradiction. OK? Yes? Sorry? On VK. No, but what happens is the limit of these guys, I can prove that this is uniform. And now, if you look at it, and this is an exercise in Matila, if you're in N, Rn, and you have an N uniform measure, then the support has to be all of Rn. Okay? So that's why it is. But that's why I also need to project. Okay? Did I answer your question? More or less. Clearly I need to. Okay, we can talk about it. Okay. Any other questions? Okay, so let me finish there.